Okay, thank you, Jian. So yeah, thank you for having me here. So I'll go directly into the talk. We work a lot recently on graph neural networks for brain imaging, especially brain connectome analysis. Today I'll be talking about three of the earlier works and the more representative ones. There are more, and I'm happy to talk more after this workshop. So the first work I'm going to talk a little bit about is called BrainGB. It's a benchmark, like the first like a graph, like a brain graph benchmark for mainly for like machine learning researchers to develop like a more advanced like a graph neural networks for brain connectome analysis. So this one is like a unified and pretty scalable framework. And in this framework, we summarized some pre-processing and construction pipelines to construct both the functional and the structural brain networks from MRI data. And then we also decomposed the design space of GNNs and studied what could be the best design choices for each of the space. And then we conduct a lot of empirical studies to show what designs could be the most useful for like a brain network analysis. So this is like how this framework, what this framework includes, from both like fMRI and SMRI. We included a pretty standard pre-processing pipeline. The goal is for any like machine learning researchers to be able to pre-process this fMRI and SMRI into like brain connectomes, brain network data. And then we apply graph neural network and study the different components and evaluate this like predictions based on the some clinical outcomes biological genders and some disease outcomes. So we conducted these empirical studies in several of these spaces, right, and showed what could be the best design choice for each of them. And we opened this benchmark on a website hosted at Emory, and this website includes tutorials, examples, and different imaging pre-processing instructions. And this pipeline can be also installed by PEEP. And also we recently also held a few workshops and tutorials such as in the big data conference last year and the ISBI conference this year to talk more about the details of this framework. The second kind of work I want to introduce was this effort on interpretable graph neural networks for brain connectome analysis. So you probably know a brain network or the brain connectome graph is basically a graph with brain regions at nodes, usually 100 or a little bit over 300 nodes, right? And then we want to build an expandable graph neural network, and the existing graph neural network usually are used for node level predictions, and also they don't consider some unique properties of the brain networks. So in this work, we want to leverage the prediction power of GNNs, and in the same time, we want to make use of the real unique properties of brain networks to make the interpretations more useful. So what we did here is the brain networks are pre-processed by usually by a lot of steps followed by a atlas-based parcellation step, right? So that basically converts the images of different samples, different subjects into a graph of a fixed number of nodes, which is the number of ROIs, right? And also fixed order of those nodes. So everyone's ROIs are ordered by the same order, right? So this is a unique property compared with graphs of other domains, like a graph of a molecular, a graph of a protein, right? So these different graphs can have different number of nodes and different meanings of the nodes as well, right? But brain networks is that all of the samples share the same node system with the same numbers of nodes and identities of the nodes. So based on this, we designed this mask-based interpretation. So basically, the idea is we learn a shared mask across all of the subjects. And this mask will be able to highlight the connections, highlight the pairs of regions of interests, which are important given an outcome, right? For example, like the outcome could be like a biomedical gender, then we want to find what are the important connections that make this difference, right? That can lead to different predictions to the two genders, right? So this is the idea, and I just skipped all of the technical implementation details, but just to show some results here. So the brain network like backbone, the graph neural network backbone, reached a pretty good performance, and that backbone basically is very close to the best model we got from the BrainGB benchmark. And then the BrainNN explainer is the model we developed here with that mask function that is able to generate some like a group level interpretation. And this model itself also gives better like prediction performance on several brain connectome datasets. So we studied this particular like three kind of datasets to predict HIV, BP, and PPMI from the brain connectome. And this mask function, this mask we learned is basically visualized here, right? So from this mask, we can see differences between like healthy control group and the patient group. And also we verified some of these differences with our clinical collaborators and some of the existing biomedical literature to verify these differences really make sense for the outcome. And the other work I wanted to talk about was this FB NetGen. It's basically more about integrating the idea of generating graphs, right, together with making predictions on the graphs, right? So the idea is you have fMRI data, and again, there's a lot of like pre-processing steps that lead to the output of time series data for each brain region, right? This time series data is called the blood oxygen level, right? The BOD signal. So we have this time series, and this would be the input we use for each ROI. And the idea would be traditionally, people, after getting this time series, right, they will compute the Pearson correlation or some partial correlation to construct the functional brain connectome, right? But what we want to do here is we don't want to use the correlation on the whole like time series, because that will like that will ignore some of the subtle differences and also the temporal patterns inside these sequences, right? So what we want to do is we want to use a time series kind of encoder, machine learning model that is particularly designed for modeling the temporal data, sequence data, right? And we use this temporal encoder to get a time series feature and then compute the graph, construct the graph based on basically correlations or inner products of this time series encodings, right? And we get the matrix out from there. And this would be a matrix that is learned from the input of the time series, right? So it's not simply the Pearson correlation computed from the input. And we make this an end-to-end pipeline. That means we further construct like a graph predictor, right, based on the graph neural networks we developed before. So we can make this whole process end-to-end from the time series to the clinical predictions, right? So this whole process can use the clinical prediction signals to supervise the learning of this graph structure. So the graph structure is aware of the prediction. So the graph structure really reflects what important connections can, again, make the different predictions, right? So this is the overall framework. So again, I ignored many of the technical details and just want to directly show some of the experimental results. So we used the two datasets. One is called a PNC dataset, and this one we make predictions on the biomedical gender. And the other one is the ABCD dataset, and we make predictions on the biomedical gender, so a biological gender. We know this prediction task is pretty limited, and recently we are also exploring the other tasks. But this model, because it needs to learn a graph and needs a lot of training, quite a lot of training, and also quite a lot of supervision. So we used this biological gender task, which has more clean training data. right? So for this task, we reached a much better performance again compared with different types of traditional model. Like we only use like a time series encoder, but not construct the graph, right? Or we use some like learnable graph construction model that doesn't really leverage the some properties of the brain connectome or leverage model the time series data. Right. So we reach better performance, and we also showcase like what could be some like potential insight we get from this model. So Pearson correlation is the traditional way to construct the graph, and we can get the graphs like in this way, right? We ordered this ROIs based on the functional module, and we can see like there are more connections within certain modules, right? Which is commonly known like for functional brain connectome. And these are the graphs we learned. So one thing is we learned much sparser graphs. So many of the connections were not important, at least not important for making predictions on the genders. We were able to remove them, right? And some of the connections, for example, some connections within the default module, right? Some connections within like the visual module, these are known to be kind of related to the gender, right? But not like but not at the specific connectome level. So that means we are able to get some insights that are partially verifiable by existing knowledge, but there are more details of this like knowledge that were not like analyzed by existing literature. So this could be some like a new insight that could be like further analyzed or lead to certain like certain things related to like treatment if it's about predicting certain diseases instead of genders. Right? So last, I want to talk about some issues and directions, especially future directions, as we want to talk about in this workshop. So some of the research problems we are currently working on includes how do we really develop more neurology-driven like graph neural networks? Meaning, how can we incorporate some of the neurological knowledge into the design of the framework, right? So the first thing we are kind of working on is we want to build simpler graph models, especially graph transformers. But graph transformers, they are powerful, but notoriously complicated, right? Need a lot of training data. So we want to be able to design some of the pathways to make the transformers simpler, right? To make them, for example, if we know some connections, some regions might be important towards a certain disease, we can make the connectomes involving those regions more like having an edge, right? And then we learn the edge there, not everywhere, like pairwise across the whole brain, right? And then we are also doing like so the work I showed, the last one, we tried to learn the novel like connections, right? But we are also trying to learn the novel ROIs. So we want to do like a learnable parcellation. We want to also use the downstream task to guide the parcellation step. And also for temporal, like for the modeling of the temporal data, these days we are also trying to do like discover the causal relations between the regions, and also we want to discover the mental states of the within each like fMRI scan. Right? And then we compare the fMRI data of the same states, not across the whole like the whole scan. So also, we also want to develop like a more data efficient training of graph neural networks. Like we are doing, we are also enhancing the benchmark to try to build larger data. In the same time, we are also trying to build like transfer learning, meta learning, and federated learning pipelines, which can make the training of make the usage of the data more efficient, right? And finally, there are like nowadays there are foundation models, and we are trying to build like bimodality foundation model, for example, by using some paired like language and imaging data to align the foundation models to make them able to make large language models able to understand like imaging or at least some time series data, right? So these are all the important research problems we are working on. Data-wise, impact-wise, I think we are trying to build like machine learning models, more advanced machine learning models, and I think this will not hurt like really hurt statistical learning, but make more like room for like for the advanced models to be to show their performance and show their like what kind of insights we can get. So yeah, that would be the end of my talk.
Questions and answers at the end of this session. So next speaker is Fei Jiang from the University of California, San Francisco.
Hello. So sorry, it's not about deep learning, but it's more related to today's keynote talk. So I'm going to present a dynamic resting state functional connectivity, how to extract this connectivity through a time-varying dynamic network model. So the motivation for this study is from Alzheimer's disease. Currently, there are more than 5 million Americans living with Alzheimer's disease, but there is no effective treatment. Proper intervention at the pre-symptomatic stage is the only way to prevent severe Alzheimer's disease symptoms. But the problem is that how could we evaluate the effectiveness of this intervention? So there are two ways, commonly used ways. One is by cognitive tests or by some image biomarkers. They are either some kind of subjective or it's too expensive. So that's motivate us to consider some other neuroimage tool like EEG, MEG data, those are the neurophysiological data, and also the fMRI data. So one particular feature we're interested in is resting state functional connectivities. This resting state functional connectivity explains how the brain region work together during the text-free mode. The resting state is text-free mode. So there are a bunch of researchers has been focused on this, and a lot of method has been proposed to extract functional connectivities. In the end, the people actually, there are some converged literature saying that the functional connectivity can fall into different categories. The resting state network can fall into different categories. Those are the researchers on the healthy subject. But the problem is that in the Alzheimer's disease patient cohorts, they didn't find converged evidence to say that the resting state functional connectivity is a confirmed biomarkers that can distinguish Alzheimer's disease patients with healthy controls. That's motivated us to take a close look at the data. So because we are actually collected the time series data, can we study the dynamicity, the dynamic resting state functional connectivity? Let's explain how the resting state functional connectivity change over time. Usually people believe that dynamic RSFCs contain two components. One is a spatial component. Let's explain, capture the links among the regions. The second is the temporal features. Let's characterize the brain state switches over time. The goal for current project is try to extract the dynamic resting state functional connectivities from neuroimage data. The second question for us is that which kind of neuroimage data we need to use? There are a few kind of functional data. The first one is the fMRI data, but the problem is that the fMRI data has low temporal resolution, typically just 2 or 3 seconds per slice. It's not sufficient to capture the microstate changes. So we've switched our focus on this EEG, MEG data. Those data have a high temporal resolution, like the 250 to 1000 hertz, meaning that you can collect the 1000 data point per second. But the problem is that this has a low temporal resolution. Typically for EEG data, the normal EEG data is roughly taken by only 20 sensors. For the MEG data, it can go to the 300 sensors, but it's on the scalp, it's not inside brain. So in order to study that, we first using some clinical validated tool called source localization in order to project the scalp data inside brain. So this clinical validated tool has been currently used in the surgery planning for epilepsy patients. So the idea is that if you have some kind of spikes or the abnormal waveforms, you can use combined with MRI data to project the spikes or this abnormal waveform inside the brain. So we use this tool to process the MEG data. The MEG data, like roughly have 300 sensors. So the simple idea is that first you build a forward model based on the autonomy of brain. So those using some physics constraints or physics formulas to do that. And then we use this kind of linear equation. This is observed data. And this error is we call lead field matrix. We can solve the inverse problems to solve this as is the source time series inside brains. Usually when you solve this, you will have around 10,000, 20,000 voxel inside brains. The second step is that we do the normal, to do the dimension reduction to average those voxels to the brain region of interest for analysis. So now leave to the statistician what is the problem we want to solve. Is can we find the connections among brain based on this time series data, high dimensional time series data, and can we find the brain state switches over time? So that is come to our statistical models. First, we assume this is called TVDN model, time varying dynamic network model. We assume that there's an underlying sequence XT. And we assume we did not observe true XT. We have observed some noised version. That's why he adds some random noise. This can be from the probability error or some kind of observation errors. The second step is that we assume the jumps of x at time t or the derivatives. It can be represented by a times x. The a here depends on time. So meaning that the a can change over time. The relationship between the regions can change over time. If you specify this a to be static over time, it's reduced to a so-called network diffusion model that has been proposed in 2014. So now take a close look. The AT is a square matrix. The AT is a square matrix. So you can always do the eigenvalue decomposition of the square matrix. So once we decompose it, the U here can be represented the RSN, the resting state networks. And diagonal matrix here, this is called the weight function, is represent the importance of this network. And RSN is fixed. We assume it's fixed because it represents static spatial features. And we assume this lambda can change over time because we assume the weightings change over time. And also additionally, what we do is that we assume each element of lambda can be a piecewise constant that can be represented brain state switches. And also lambda is a low rank matrix. That's just for estimation convenience. And this model actually have a very good interpretation. This can associate this model with the growth static constant per second, and okay, can associate with the signal frequency. So that's a recap. What we have is that first is a noise model. The second is the diffusion model, and then is how we decompose this A matrix. We propose some algorithms to solve this to estimate the parameter, the important parameter of A and U. The first, of course, we want to remove noise. We just do the simple piecewise smoothing to get these X and X primes. The second step is that we use a kernel feedings and add some penalty on this A matrix to get the estimator of A and extract the U matrix from this A. And also, if you take a look at this A matrix, you can decompose this to U lambda, U inverse. We can easily have this dimension reduction to reduce the dimension from the 68 region of interest to R. So then we do the change point detections by minimize this the modified BIC method. Essentially, the first component is just a negative log likelihood, and the second component is penalize how many switches we have, brain state switches we have over the time. Finally, if you have all the switches and you have a stationary pieces, and you can estimate the lambda matrix by just simply minimize these mean square errors. So we actually implement this method on some test-based data. So this is a student actually sitting there taking the eye closed, eye open data, the test, and you can see the red line here essentially is the time point that he was open eyes or closed eyes, and we use this method to detect the event times, and you can see that our detection is very close to the truth. And we also implement this method to the like 243 fMRI data. So that is on the healthy subject. So first we want to try to see whether the TVDN method, our method, is actually performed similar to the sliding window approach to capture the spatial features. And the first showing that they actually show you the pretty similar spatial features. And also we studied the kind of prediction accuracies between our method and the other sliding window approach, meaning shows that a TVDN method has smaller prediction errors. Later on, we have another paper to apply this method on our current cohort. Our current cohort has 88 80 samples and 88 control, age-matched control samples. Those are from the MEG data. We extract the TVDN scalar features, that is the number of eigenmode, that is the number of eigenvectors, and also the brain state switches. And also we extract the spatial feature, that is the average weighted resting state network. What we can show that we find some important feature, features. One is the number of eigenmode. The second is the 80 subject always have a higher number of eigenmode. Implies that 80 subject may have a more complex brain state. They have more state than the healthy controls. And also the 80 subject can have a few state switches that we can consistently observe that both in MG data and EEG data. And we also project this average RSM onto the brain. And this brain regions actually reflect the high tau accumulation regions. We also compare the sensitivity and specificity for distinguished AD and control samples, although it's not very interesting for the clinicians, but it's shown that our method is better than the sliding window approach. So finally, I want to conclude my talk is we find a potential biomarkers for the Alzheimer's disease to early detect Alzheimer's disease. The problem is that we need more longitudinal studies. Now in this field, in neurodegenerative field, people always, like physicians always claim we need longitudinal data to know the baseline of the patient. And then we can use this longitudinal data to track the patient to see whether they really have a neurodegeneration. And also I want to answer a few questions was written by the organizers. The first is what's the most important research problems in the next few years? I cannot say from broader views. From my perspective, I think analyzing the neurophysiological data can be a good field because neurophysiological data, you can hardly read neurophysiological data. It's very hard to kind of understand the meaning. The algorithm is more accurate than human readings. So that is the reason why I kind of advocate to study neurophysiological data and some kind of physics informed deep learning because many neurophysiological data is based on some kind of physics process. It's even for the data we use when we do the processing. So we have a built-in model that is a physical process. And also the second question is how can the statistical community improve the processing and sharing of data? Of course, the first step is building the reproducible tool. And the second is that disseminate the tool in the non-statistical conference. So that is my suggestion of my experience. And the last one is how can we make a statistical method more impactful in imagery community? I think the collaboration is very important, finding the good collaborators and finding the 0 to 1 problems instead of kind of working on popular problems. So that is my kind of suggestions. Thank you.
Okay, we have time for one question.
Your model is stationary model for resting cell. The composition.
Yeah.
That's a stationary model.
It's not a stationary.
The variability of Y in your model.
So we didn't examine that. We need to go back to the data to check the variabilities. Yeah, but we do the processing first. So it's actually the source localization algorithm essentially reduce a lot of variations in the data.
Thank you.
Just a quick question. Do you fit your model to a single subject or do you fit model to multiple subjects at the same time?
We fixed for single subject.
Single subject. But do you do analysis across subjects?
We do the analysis across subject.
To combine those analysis, I would expect probably quite a lot of subject variability.
Yes, definitely. In the end, when we apply to the Alzheimer's dementia cohorts, we essentially just extract a few features from our models. Like I present, it's just the number of switches and the number of eigenvalues. Extract those summary statistics and then do the population level analysis.
All right, thank you. Okay, let's move on to the next speaker. Our next speaker is Linglong from the University of Alberta.
So today I'm going to share with you about a methodology we recently proposed. It's on double adaptive spatial quantile regression model for neuroimaging data. And unfortunately, this is not a deep learning either. So, um, first I do some introduction, then our methodology. I have some simulation study and real data analysis. And for neuroimaging data, we all know we have this sort of multi-image and multi-subject. For the same subject, we have multi-image, then we can do the sort of first level analysis for individual. And then for multiple subject, we can do this sort of second level analysis, group analysis. In my project, I focus on this sort of second level analysis. In particular, we have response located on this 3D space. And for example, we could have gray matter, white matter. And then we have some chlorides, and we have this, let's say, gender, age, diagnostic status, and maybe also some genetic information. And our goal here is, so I'm trying to estimate the covariance effect, trying to identify those region of interest. Not only that, we also want to test it to see whether it's statistically significant. Then afterward, we want to see whether it's also clinically significant. Now, for those kind of method, traditionally we have voxel-wise method, let's say, and we ignore the correlation, spatial correlation, just do this voxel level analysis. Of course, it's the result is consistent, but it's not that efficient. And we can also do this sort of spatial modeling. And for example, we can have some spatial correlation prior and so on. And however, for this kind of method, it can computation, it can be very, very intense. Of course, we can do something in between. For example, we have this propagation simulation method, and it's great, but it may also ignore the variability of image data. Now, in particular, if we go back to look at the whole process of like statistical analysis of image, our job is at the very end. We first get the image, and then we do image processing. That get involved physicians and applied math, CS engineer, and then at the very end, as our statistician, we may have very handy data, very neat data, then we can do our statistical analysis. However, during this pre-processing, there may be some inconsistency. We always see like paper from neuroimaging, we use our house processing tools, and they may end up with some inconsistency. That's one thing. The second thing is, although statistically we always assume the underlying error is Gaussian for convenience, for theoretical reason, but in reality it might not be. So all this makes this sort of a quantile regression. We model the conditional quantile instead of the conditional mean more appealing. Not only that, for quantile regression, we can also have a better picture, have a full picture, not only the center, how the center change according to covariance, but also the tail. Therefore, in this project, we propose a double adaptive spatial quantile regression model. And for this method, we are updating our estimate by borrowing information from nearby voxel. And in addition to that, we also borrow information from nearby quantile levels. So our underlying assumption is the response it changes with covariance piecewise constant or piecewise smooth in terms of voxel level, and also piecewise continuous in terms of the quantile level. That's our underlying assumption. Now, in particular, this is how we model the quantile, and we try to model the Tau's conditional quantile given some covariance and satisfy this this condition. And therefore, we can use this is a quantile log function. We can use a lot of methods nowadays to do it. It has been implemented in many softwares. Well, for our double adaptive, like I said, we want to borrow information from nearby voxel. We want to borrow information from nearby quantile. How do we borrow those informations? The borrow information part is coming from these two weight. One is WDD prime H, one is W tau K B. So we borrow nearby voxel, this D prime nearby voxel in a block. We borrow nearby quantile, this tau K, it's pre-specified. Now, how we determine the weight? The weight is coming from two parts. So one is related to their location, location in terms of voxel location, in terms of quantile location. So this is local smoothing. We borrow information through this kernel. The other one is coming from smooth, and the smooth part is based on this similarity, and it's based on how close the estimates are. If the estimates are very close, then we should borrow more information. If they are not that close, we should borrow less information. In this way, we can respect the data of this piecewise continuous within certain region. They might be continuous, or within certain quantile level, they may be continuous. And also, because of this second term, we can also separate them. If the estimates are quite different, then through the second term, we can borrow less information. Therefore, we can separate. So eventually, we can do a little bit of organize, and it becomes this single loss function. And here we have a weighted quantile level tau star, and we have this transformed response and covariance. Now the whole process gets three steps. Initially, we do this initial update. We do it at a quantile level and a voxel level, and then we do a weight update through this propagation separation. And once we get the initial estimate, and the weight depends on the estimate, so we can update the weight through these two kernel function. And then once we update weight, and we can plug it into our loss function to update the estimate. And then we continue this iteration process. Of course, we have some stopping, checking. And the reason is the estimate is already consistent. We don't want to be too far away from our consistent estimate. Now, in particular, for the propagation separation process, and we start with each voxel, we do the estimate, then we have a bar, and we look at the nearby voxel. Then after we get the initial estimate, we can update our weight, and then we get the updated weight. We look at even bigger bar, trying to borrow more information. Now, the stopping rule, like I said, we got to stop. We don't want to be too far away from our initial estimate because it's already consistent. Our goal is just trying to make the variation smaller, make the estimate more efficient. Now, of course, that's the whole procedure. We have some certain theoretical property, including the first consistency and asymptotic normal. It looks very like regular. You just get the consistency, get this asymptotic normality. However, this process is quite complicated. The verify of this theorem is quite challenging. And then we also have two theorem in terms of this dissimilarity and also this kernel function. Those two theorem guarantee that we would be able to first identify those regions of interest if they are similar, and we are able to identify those regions, and also we do the separation if they belong to the different region of interest. We are able to identify the jump, identify the edge, and then the very last theorem is also very important. We said, okay, the initial estimate is already consistent, but we want to improve our efficiency. In a sense, we want we want to improve the power, we are able to detect these important regions. So how do we realize that? How do we accomplish that? We need to make this covariance matrix to be smaller in order to be more efficient. And here we indeed prove that if we do this process, our covariance estimate will be smaller. In instance, this is the original covariance matrix. This is the updated covariance matrix, and the difference is a positive definite matrix. In instance, we indeed improve our initial estimate by makes the covariance matrix smaller. And then we have some simulation, and here is our simulation model. We have a location scale model, and we have a covariance 1 and X2 and Doubly. We mimic this categorical data, and X3 is uniform. We mimic continuous variable, and this BD is the coefficients, and BD belong to 0, 0.2, 0.4, 0.6, and 0.8, indicate different effect size. So eventually, we have this beta 1, beta 2, beta 3, these 3 underlying truths of the covariance. This is the first row. As you can see, we have different regions. The blue part mostly 0, and we have 4 different regions. And this is a tau equal 0.5 center and tau equal 0.3. And the second row is the initial estimate. As you can see, we the initial estimate may miss a lot of region of interest. And here the third row is the updated version. And as you can see, we are able to identify way more a region of interest than the initial estimate. Of course, we have some other measures, and here we see the variance indeed get decreased, and we look at these p-values. Okay, and then some numerical result. I'm not going to go through it. Now, at the beginning, we said, okay, we are trying to deal with also 2 things. One is the inconsistency of this pre-processing. And here we are trying to mimic the inconsistency. In particular, we have the response structure randomly about 20% get shaped 1 to 3 voxels, so that let's mimic this imperfect, for example, alignment and so on. And we still get a similar result, and this is the initial estimate. This is the updated estimate. We get way better result than just the initial estimate. And another thing is we mimic the situation. We may have the data not perfect. In sense, we select 20%, and we multiply it by 10. Then we get we also get similar result. An initial estimate, as you can see, is quite worse than the previous one. However, after we do the our smoothing, is we can still recover a lot of a region of interest. And then we actually did this ADHD in particular for this ADHD data because we know this ADHD data have a very weak signal. We are trying to see if our method be able to identify some region of interest. Indeed, we do. I will just show you this very last result. And this is from the initial estimate. Those are the important voxels we identified. As you can see, for the number of voxels, it's very, the region is very small, like the only top three get more than 100 voxels. While using our method, we can identify a bigger and more voxels, more region of interest than previous one. Okay, I think I will stop here. Thank you.
In the passion and our session, let's move on to our next speaker, Professor Wang from George Mason University.
All right, so first I'd like to thank Jian and Hongtu for bringing us together here. I do feel privileged to be here and share some of my thoughts. So today I'm going to share some challenges and insights in deciphering massive high dimensional data. We all know that recent advances have revolutionized the neuroimaging field. We have a lot of advancement in data acquisition and data analysis. So along with all the opportunities, statisticians also face many challenges. So I'm going to share some of the challenges based on my research experience. The first one is the exploration of high dimensional imaging data, where traditional statistical methods suffers from the curse of dimensionality. And in addition to neuroimaging data from multi-modalities, we also work with other imaging data such as genomics data and clinical data. Integrating these diverse information together pose another very significant challenge. And the third challenge lies in data complexity. We know that imaging data typically contain unwanted noises and also very complex spatial and typal heterogeneity and correlation. So we need to have a sophisticated model to capture the underlying pattern and heterogeneity from such complex data. So we need to develop a method and refine and tailor the methods for such kind of data. Another challenge I want to spend some time today is the verification, validity, and uncertainty quantification, the so-called VVUQ. These are significant challenges for many different fields. For example, I think in neuroimaging studies, let's say, we try to locate and identify the difference between two groups of images, or identify the significant effect of some treatment. So we need to develop a rigorous statistical inference tools to understand and identify those differences. And also the technology of generative AI significantly add another complexity of to this kind of analysis. So a key issue here is how we can verify synthetic images still maintain the quality and the characteristics of images. And this leads to a very important question: how can we compare the real images with AI-generated synthetic images? And the last challenge I want to talk about today is the computing. We know that for many of you, you deal with the neuroimaging data. A typical 3D scan, it contains 100,000 voxels. And then you multiply by the number of time points and the conditions, and then multiply the number of participants. You can easily get 1 billion data points. But it does not just stop there. With the advent of generative AI, we can easily get tons of synthetic images to augment our data. So these generative AI techniques amplify the challenges of computing. And on the other hand, we are facing disparity in computing resources. many institutes like us, we don't have enough computing power or resources, following much behind our industry. So in the following, I'm going to share some of my recent research project on distributed imaging scalar regression to illustrate the challenges I mentioned before. So the overview of the project is try to understand the relationship between imaging phenotype and a set of predictors or explanatory variables. And we try to develop a scalable and interpretable framework to understand this relationship and identify and locate the significant effects, if there are any, or any difference. So I'm from the functional data community. So for the model, I'm going to consider the traditional image on scalar regression. And this model has been studied by many different authors for sitting here. So what we have an imaging phenotype on the left-hand side, and we try to regress it to the scalar predictors, such as environmental, genetic, or their interaction. And this model is also called a spatially varying coefficient model, like Linglong just mentioned. So the coefficient actually vary with the location. So it's called a spatially varying coefficient model. And we try to develop a simultaneous estimate and make inference of these coefficients. So this is a procedure of our model. So for some of you in functional data, so this might sound very familiar. So start from the imaging data, you can try to estimate a coefficient function. And then based on the coefficient function, you can find the residuals and then construct the covariance function. And then based on the asymptotic properties, you can obtain the point-wise or simultaneous confidence intervals. So this is a very typical procedure for functional data. But when we're dealing with new imaging data or large-scale medical data, we face the computational challenges. So to address this, what we propose is a distributed learning and inference approach. And our approach is based on the triangulation. And there are a couple of advantages using triangulation. First, it can approximate a very complex shape of the object, such as domain, the brain domain. And second, it can also facilitate the domain decomposition for parallel computing. So this slide shows you a definition of the triangulation and also an example of the triangulation for the brain domain. I don't have time to talk about details. So you can look at how to construct a triangulation based on our recent GMLR paper. So based on the triangulation, we develop a distributed algorithm to do image on scalar regression. So we start with our master process. It will read the entire instance and distribute the data to the subdomains. So we may have many computer nodes or workers. And then for each worker, it will use the data in the related region and then feed the model and return the corresponding estimated parameters to the master process. And the master process will aggregate and do some adjustment if necessary and give you the final distributed estimator. So to evaluate our method, I'm going to demonstrate some simulation results. And the first one I choose to show is based on Jian and others, the 2023 GISSB summer courses are here, Jian and Lexing. So this paper has set a very high standard for using neural network. So I'm trying to use their simulation study to illustrate our performance. So following the paper, we generated 3 coefficient functions. These are the true functions. And then we apply our distributed Spatial regression methods, and this is our estimated coefficients. You can see it can capture some very complex pattern that can be done by neural network. And in terms of numerical comparison, our method is similar to the neural network method. In some cases, we're slightly better, especially in terms of computing. For our computing, we use 16 CPU cores, and our method can be done within 5 minutes, which is in contrast with the number of hours done by a neural network. In the second part, I'm going to talk about uncertainty quantification and statistical inference. I'm going to use two very quick examples to demonstrate some ideas. The first one is still the distributed image on scalar regression. So we consider the 3D PET image scans and consider a set of interpretable variables. And then we build a regression and we try to look at the significant effect of those explanatory variables. And for the computing, given the challenges, so we use a distributed learning based on 16 workers. And this is the triangulation we used to obtain the results. So this is the estimated coefficients of the variable age. So here, the blue color indicates the regions that with decreased metabolic activity. And based on our method, we also make inference. So on the right-hand side panel, we construct simultaneous confidence regions. And based on the confidence regions with different confidence level, we can identify and locate the significant regions. And the second example I'm going to show you is how to compare real and synthetic images using statistical inference. So you may ask, why don't you use a global metrics such as FID and word stand distance? This is very good, very helpful metrics. However, they tend to show the overall similarity without giving you the detailed effect of differences. So what we try to do here is to do a more granular analysis and to build inference tools and examine exactly where the difference is. Just to give you a little bit taste. So for example, let's say we are interested in testing the mean difference between a set of real and synthetic images. So here you can use our inference tools such as simultaneous confidence regions. We can locate the significant difference between the two sets of images. And then we can use this information to fine-tune the AI model and improve the quantity and quality and reliability of the model. This work has been done by a group of students. I think Zhiling is right here. She's going to give a poster on Thursday. And some other students also made a significant contribution to the project. So finally, I have 1 minute to share some thoughts about statistics impact in imaging community. So here are some strategies based on my research experience. So first, I think somebody already mentioned that we need to work closely with domain experts and also computer scientists. We need to engage with the domain experts and join their research projects so that we can make our methods more relevant and applicable. And second, we need to tailor our research methods for imaging data and develop tools for data fusion and integration. And we also need to make our models and research work more reproducible and promote open science practice. And spend time to develop accessible tools, especially integrate some of the well-developed tools with popular imaging platforms. And then embrace the current AI trends, develop AI methods, and make sure our statistical principles are applied in the development. And finally, I want to say contribute to the setting of the standards and also verification, validity, uncertainty quantification, and this can make our statistical methods more impactful in the imaging community. So that concludes my presentation. And thank you very much for your attention. And I look forward to share results through the rest of the conference. Thank you.
Discussion. Any questions, comments? Yeah, Weixin.
For this project of comparing the real and synthetic imaging data, I'm just curious what kind of generative tools you use to generate those images.
So Zhiling actually no better answer. So we actually tried a couple of methods, like again, diffusion models. I think the one I'm showing you in this slide is the diffusion models.
You develop those tools yourself, or is some kind of
We
existing?
use some pre-trained method. And for the presentation, I think Zhiling actually tuned the training. She's right there. So she can tell you the more details.
Questions for Lily, and we open the floor to for this session. So we have 4 wonderful speakers, and if you have any more questions, feel free to ask now.
For Linglong, just curious about the quantile regression. I don't know much about it, but I know the one thing that's annoying is when you have crossing quantiles. How do you deal with that? Is that a problem for you?
For the crossing quantile, for the crossing quantile, it's his name in MIT, I forgot his name. I had a very good paper in terms of how to deal with the cross quantile, which is reformulate if. But on the other hand, if the data is large enough, you have enough data, usually you won't have this cross quantile. And if you do, then you just reformulate it. And usually it's an effective way to deal with.
So did you estimate the parameters simultaneously across different?
No, actually here we select, let's say in my project, I use tau equal 0.5, then I select about 10 quantile level around 0.5 and then do. So
your result can guarantee the monotone pattern of quantiles?
No, I cannot. Like I said, if they do cross, and then you just repermit. And if you just look at one quantile, then that's fine. If you do multiple quantile, they do cross, then you just repermit.
But your theory have this consistency. That means samples are large enough, you can guarantee that, or?
Yeah. Thank you.
No.
I have a question for Fei. Fei, very nice presentation. Are you using your model on the resting state data? So earlier, Lucian asked you about combining results across different subjects. Now, if you're using resting state data, there's no well-defined, they're not time locked to a stimulus, right? So how would you, what is your idea about combining information across results across different subjects?
Yeah, actually it's not, well, when we do the estimation, it's not kind of integrate all subject. What we do is just the subject by subject to extract some of the features and then compare the feature difference across the subject. The second one is more kind of apply work. We develop these tools. We want to see whether it can find anything in our Alzheimer's disease cohorts. We definitely find that some of the important features. But later on, so what we are doing is that we're still collecting the data. So later on, we probably will have longitudinal data to validate whether this is qualified by markers for the detection.
And so because it's not time locked to a stimulus, therefore your features will not have the time information anymore.
Yes.
Okay.
Yes.
Thank you.
Any other questions? Or comment? Yes.
This is a question for Lily. The last graphic that you had, oh, here, the last graphic that you had, it was really nice and touched on similar concepts that other people presented. My question is, do you have any ideas or advice on what career stage should tackle each of those? Because I mean, my point is, so I'm later in my career, but I was thinking, you know, I remember as an assistant professor, one of the main goals was to get papers out and, you know, first author papers. So being on these huge collaborative team is wonderful, but if I'm 20th author, it feels like a dent to my career.
I understand.
So yeah, I'd love to hear your thoughts.
Yeah, so this slides, I know just try to address the questions that Jian mentioned, how we can statisticians increase the impact in imaging community. So may not be tailored to each individual. So I appreciate what you just commented, like different career. We do have a different kind of a focus to do, but I think it's very versatile. Some cases like develop user-friendly software. I think this one I deeply promote it because I feel the product is very important. During my experience working with the government agencies and many collaborators, I found what they usually appreciate the most is the final product. So I would suggest our statisticians could spend more time to work on it. We can talk more to share more thoughts after that.
Thanks. More questions or comments or general answers to the questions about deep learning research in our field?
Yeah, as a general comment, question really for Lily and for the others in the audience about the use of synthetic imaging data. So it's to me it becomes very scary. I attended a class on natural language processing, and you know, so how one would predict the next word in my sentence that is derived from some empirical distribution, and where I really have no control as to whether or not that distribution is filled with misinformation or correct data.
Yeah.
So with respect to generating synthetic data, I'm wondering whether one should look at just the distribution of the observed imaging data or that distribution condition on all the other covariates that are actually observed. And therefore, if you want to check for the fidelity of the artificially simulated data, then next, how would you actually compare whether or not your artificial data is is close to the true data? Should you look at only the image itself, or should you look at the conditional distribution of the image? You know, that condition on the other covariates, gender, disease type, so on and so forth.
So first, I would say you raise a very important question, and I do share how scared of statisticians when we first started to work on with the generative AI methods. So my group, I have a lot of students working on the pre-trained models, tons of time, and to tune the model and figure out some of the methods is a big failure. You mentioned many interesting problems, I think, for statisticians to work on. Our group, we just started, and there are definitely many important directions, like you mentioned. Actually, we do the conditional or unconditional, or conditional on the other covariates or information. I think we can consider different directions. But overall, I feel like statisticians need to embrace these methods. Try to work with computer scientists and also domain experts and to figure out the most important problems. And some problems maybe we feel very important and we want to do, but may not be their relevant problems. So I'm probably not the best one to answer the question, but I encourage all of us to reach out.
Embrace with some caution.
Yeah.
Yeah, I think in general, I want to make comments about the deep learning in general, why this method has been really got a lot of attention last decade. There's some deeper reason behind it. And I think if you think about neuroimaging or in general medical imaging or computer vision, and all the conferences already transfer from traditional models to everything is deep learning. There's nothing wrong or nothing right. I think they offer something big. Okay, we have the medium data fact, but I do think the people here, and the needs for next generation statisticians, students need to learn how to do it and how to use it properly, and think about why should we use it in some scenarios. That's that. The one thing is, our department at NIST, we try to offer these kind of courses. I encourage all the students, master PhD students, to take the course. Because I think even in the GSM has more training courses on that. I tell you a fact, if we think about what the deep learning has changed the medical image or computer vision, the number one problem is segmentation. Okay. You basically think about that's the most important things in the medical, in general for image analysis, because they identify the features of your interest. And also relate to statistics from modeling aspect. If you think about the functional data analysis, I think the deep learning can handle heterogeneous signals. This is basically the traditional functional data analysis modeling have some problems, because you think about like tumor. A tumor could have happened in have a different size, different location, all the things. And basically you can use the pre-trained models to easily handle it. And basically that's the mapping. You change the unstructured data to the structured data. Then they do the traditional statistical analysis outwards. It's not to say they completely replace, but they do offer something better than the existing ones. Okay, you don't have to say I dig into all these mathematics, using the functional analysis tools to do it. These days don't have to, because when you handle the heterogeneous signals, that's what will be the case. But I think that I would love to see more of the people using the deep learnings and to solve the problems. Okay, but it doesn't mean that statistical thinking is still the most important things when we develop this model. There's a difficulties. I don't usually, I'm not a fan of use the diffusion model to simulate the medical imaging data. Okay, those days the companies or the startup companies is basically for fun for kids, right? I write a text, the generator, the picture movie for. And that's the more mainly for fun. But when you talking about the medical image, I'm more conservative, because you think about we have to do something serious in medical science in general.
Maybe I'll throw a positive spin on that, which is I think that the deep learning especially has a transformational effect on the pre-processing parts, which you alluded to, the image processing. But the thing that I keep on coming back to is I keep on talking to collaborators, and they know I'm in a big data institute, and then like, well, we work for 4 years, and here's our 40 subjects, on concussions, they just, and I think in biomedical research, there's still going to be, continued need for, data sets that have two digits. And that's not, you don't want to mess around with okay, I'll split up those 40 subjects and that's my held out. And it's like, no, you're going to have to lean on traditional statistical methods that can do the best job possible with a small number of subjects.
Yeah, that was kind of my question to follow up. Can you talk about amount of data and amount of homogeneous data? Okay.
What's your point?
Can you talk about ideas for the amount of data needed for machine learning and its necessary homogeneity of this data?
Well, I think that you're talking about a very important points. I think that for deep learning, most pre-trained models come from computer vision. They have this basically annotated data set. from the tech companies. If you think about in tech companies, all the CV projects, the number one cost is the annotated data, okay? They either connect all kinds of scenarios or simulate the scenarios, the annotated data, then build the models and do all things.
Look at all the images.
And, but the numeric image, one big challenge is we don't have a really good annotated data set. And the person or company has the data set can sell that for thousands of billions of dollars, US dollars. They can become rich, okay? Because you know that it's like a tumors. If you know how to segment some of the weird tumors in some any organs, that's you can become rich just do that, okay? That's basically the key limitation in medical image. It's not the annotation is not important. It's not the number of data. We don't have the data. We do have this amount of data because you think about the hospitals, the connector radiologists, and the radiology connect all the data, but usually the annotator you don't have it. You have to have some connections. But I do think the deep learning is a right tool to handle these type of problems. If we really have the annotated training data, then sample size is big enough. And because we are dealing with the complex organs in the body and also the disease have some large variations. And when you have to handle that case, there's a traditional method won't be able to handle. Thank you.
All right, thank you. Let's end our session. It's time for lunch, I think. Thank you all for your wonderful discussion. We can have more discussion.
So our lunch will be at downstairs. So if you exit the auditorium, turn right, and then it's the stairs go down. And then you can get your lunch there. Thank you.